welcome students to this video, and in this video we are going to continue our study of oscillatory equations. So essentially, what is an oscillatory equation? So basically, if all solutions of this, we will start with this self-adjoint equation, right? Py prime whole prime plus qy equals to 0, let's say, and p and q are smooth functions. P and q are smooth, is in C1 of I, whatever I is. I can be R also, right? So this is the problem. Let's call that 1, and for p equals to 1 we have this equation, very special equation. Let's call that 2. Yes, so we defined oscillatory equation as, let's say, if you have a solution which does not have a last zero, okay, then the solution is called oscillatory. And if your equation has all solutions such that they have no last zero, then this is called an oscillatory equation. Very simple, right? And we have looked at two very important theorems. Let's just recall the theorem. Okay, the first one is called the Stump's comparison. Okay, so what does it compare? It compared the solutions. It compares, okay, theorem. So what does it says? It says that, let's say, if, so I'm not writing the exact statement, okay, that is already done. This is just for a recall. So if, let's say, q1 of x is greater than or equal q2 of x, if this is the case, sorry, q of x, okay, and alpha beta and y at the point alpha equals to y at the point beta, okay, equals to 0. Alpha and beta are consecutive, right? Consecutive zeros. Okay, such that y satisfies y double prime plus qy equals to 0. Okay, so let's say that you have a non-trivial solution of this problem y such that alpha and beta are consecutive zeros. Yes, if this is not equal, this is not equal, if q1 is not equals to q2, then we can say, please remember this thing. It is said every, not just one, every non-trivial solution z of x, okay, of which equation? Of y double prime plus q1 x z y equals to 0. This equation has a 0 in alpha beta, right? That's the Stump comparison theorem which we learned. Please remember this. Two equations are there, right? Y double prime plus px y equals to 0. And another one, y double prime plus p1 of x y equals to 0. Okay? See, what it is saying is this. If you can find just one solution, you understand? If you can just find one solution such that solution, let's say y1 is a solution of this problem, such that y prime of alpha equals to y prime of beta equals to 0, and alpha and beta are consecutive zeros, that is, there is no gap in between them. Gap in the sense that there is no 0, so there is no gamma such that y1 of gamma is 0. That's what I'm trying to say. Gap means this. Okay, so in that case, what happens? It is saying that in between, see, this is just one solution. Okay, we are assuming just one solution, non-trivial of course, because if it is trivial solution, everywhere it is 0. Okay, doesn't matter. Now what it is saying is, if you can just find one solution such that this thing happens, okay, then any solution of this problem, any solution, okay, let's say z is any solution, doesn't really matter what. If it is a solution, then z will have a gamma, let's say, between alpha beta, where z has to be 0. Is this okay? Any solution z. Of course, again, it is non-trivial, because if it is trivial, it is 0 everywhere. Doesn't matter, right? So this is true. When is it true? That you see, in the case that p1 should be, at least at some point, it should be different than p. Is this okay? At least at one point, it should not be equal. Okay, and then if you remember, we also looked at something called a Picon's identity. Okay, Picon's identity, and I have told you that this is very, very important to prove the theorem which we are going to prove today. Yeah, what is Picon's identity? So all this. Okay, so let the functions y, z, py prime. This is a big statement. So p1 z prime are differentiable. Again, and zx is not 0. This is very important in I. Again, let me tell you this. See, Peacon's identity as itself is not very important. Okay, it's just some identity which is satisfied by some functions. That's all. Okay, but the problem is this: these you can use this identity to actually find. I mean, to actually in a lot of different applications. Then the following identity holds. Identity holds. Okay, so what are this? See this identity y by z, yeah, again z p y prime minus y p1 z prime, the derivative of that, clear? That is nothing but y p y prime, the derivative of that, okay, minus y square by z p1 z prime, the derivative of that, plus p minus p1 y prime square plus p1 y prime minus y by z z prime square, right? That's the Peacon's identity. We proved it, right? We just expanded this thing and we showed that this is equals to this. So that's Peacon's identity which we are going to use today. So now see, the first term comparison theorem which we did is for this equation. Yeah, this is not a general equation. The general equation is given by this, right? You remember, this is the self-adjoint form. Yeah, so now we are going to do something called a Sturm-Peacon's theorem. Sturm-Peacon's theorem. Okay, so let me write down the statement of the theorem, then I will tell you a little history about the problem. Okay, so let's say if alpha beta in some I are the consecutive zeros, okay, of a non-trivial solution. Please understand this. This is a non-trivial solution, just one non-trivial solution. If you can find a non-trivial solution, something like this, solution y of x of 1, solution of 1, yes, and if, and this is the condition, and if p1 x and q1 x, clear, are continuous with 0 less than p1 of x less than equal px and q1 of x is greater than equal q of x in alpha beta. Okay, so that alpha beta consecutive 0 in that interval alpha beta, then every non-trivial solution zx of the differential equation. What is the differential equation? p1 of x z prime whole prime plus q1 of x z equals to 0 has a 0 in alpha comma beta. Okay, so if you look at it carefully, see, this theorem is exactly the same sort of statement which we did for the Sturm comparison principle, but that is for p equals to 1. This we are doing it for any p, smooth p, that is, but any p, right? So you see, our condition was the equation which we wanted our root to have 1 0 in between, that coefficient should be bigger than the original equation. So here also you see q1 is greater than q, exactly, fine. Now the thing is, what is the requirement on p? See, here p actually flips, so you have to have p1 should be less than equals to px, and this should be strictly positive. Yeah, this is very important, it has to be strictly positive. Okay, if something like this happens, then we can say that the exact same statement, that p1 z prime whole prime plus q1 z equals to 0 has a 0 in closed alpha beta. Please remember, it is closed alpha beta. This is the difference here. It is not open alpha beta. See why this requirement is there. I am not assuming that it cannot be same. So here remark the difference with this and stump comparison. You see here the 0 may be admitted, okay, at the endpoints also, at the endpoints. Okay, do you see why it is the case? See, the thing is this, here I am not assuming that it cannot be same, right? So P can be equals to P prime. See here, P can be equals to P1 and Q equals to Q1. If that is the case, then both the equations are basically same, right? So they will have the same zeros, right? So in that case, essentially you have to have closed alpha beta. Clear? Of course, if you are doing that not equals to, then that is different case. Okay, right? So we are assuming this thing. Now let's look at the proof. Okay. Oh, okay. Yeah, I told you that I will tell you something about some history about it. So the thing is this. This was actually done in around 1880s, 1890s by Sturm. Okay, and at that time it was called Sturm theorem. Okay, and the proof is extremely lengthy. It's like 4 or 5 pages proof. Very complicated proof. Okay, this theorem had. Okay, so the Stump used this Stump comparison theorem. That was very easy, right? Which we have seen the proof of. But when that P is involved, okay, the proof was actually complicated. So Stump proved it using basic analysis, but it was very complicated. 4 or 5 pages, as I told you. Now around 1901 or something, around that time, Picon came up with Picon's identity, and you will see that after using Picon's identity, the proof became just like half a page. Okay, so let's look at the proof. Yeah, and it actually simplified the whole process a lot. So what is it? So let's say that Z does not see. Here I have to show that there is a 0. Z has a 0 in closed alpha beta. So let's just assume that Zx is not equals to 0 in closed alpha beta. Let's just assume that, right? Alpha beta. Okay. Then we will use Picon's, you see, Zx is not equals to 0, right? So we can use Picon's here. Okay. So we Picon's identity and find, then we use Picon's identity to get, okay, what is it? Let me just write it down. I will explain to you. Y by Z, Z P Y prime minus Y P1 of Z prime whole prime. Okay, this is nothing but Q1 minus Q times Y square plus P minus P1 times Y prime square plus P1 Y prime minus Y by Z Z prime square. This is okay. This is what we are going to get. This is from that, see, from the Picon identity. If you look at it carefully, P1 Y prime minus Y by Z Z prime square, this term, okay, P minus P1 Y prime square, P minus P1 Y prime square, okay, and then Q1 minus Qy square. You see this expression and this expression. See, Z solves this problem, right? So P1 Z prime whole prime is minus Q1 Z. So minus Q, see, P1 Z prime whole prime is minus Q1 Z. So and this Z is not 0, so we can cancel it out. So it is plus Q1 Y square. So this is Y, Q1 Y square, okay, and from here you can see it is becoming Q of Y square. So minus Q of Y square. So minus Q of Y square. Clear? So very simple. Right. Now we integrate it. So integrate this expression. So integrating. Okay. The above we get what we have. See, if you integrate the above, you see there is a Z here, there is a Y here, right? And we know that Y at the point alpha and Y at the point beta is essentially 0, right? So what do we have? We have alpha to beta Q1 minus Q y square plus p minus p1 y prime square plus p1 y prime minus y by z z prime square dx. This is going to be this expression. If you remember, see, this y is there, so it doesn't really matter what is inside. Y at the point, so if you just integrate it, it will become y at the point beta times this at the point beta minus y at the point alpha times this at the point alpha, this whole expression. Okay, and y at the point alpha and y at the point beta is 0, so basically this is 0. Is this okay? Now you see, this is a contradiction. This, the above, let me write it this way, the above is a contradiction. Unless q1 equals to q and p equals to p1, okay, and y prime minus y by z z prime is equals to 0. Okay, otherwise it's a contradiction, right? See, these are all positive terms. q1 is greater than equal q, so this is a positive term, this is positive. P is greater than equal p1, see, it is given p is greater than equal p1, so this is positive. Yes, and this is a square term, so basically this is either greater than equal 0. So if this is the whole thing is positive, essentially what is happening is this, and p1 is given to be positive, right? Okay, so the whole thing is positive. Okay, see, this is the place where we are using it. P1 is greater than 0, strictly greater than 0. So you see, the whole expression is positive. So a positive expression integrated between alpha beta has to be positive. So if it is 0, it means that all these parts has to be 0 identically. So, and in that case, q1 has to be equals to q, or p1 and p1 has to be equals to p, and y prime minus y by z z prime equals to 0. Okay, see, this expression is nothing but y by z, the prime of that is 0. So that will imply y is some constant times z, right? Is this okay? Y has to be constant time. So you see, this is this expression is already a contradiction. It won't be a contradiction if this and this is true for all C in R, right? You understand what I'm saying? Okay, but now you see, what is y at the point alpha? That is 0. Okay, so that will imply that the constant C, see this constant C, this has to be 0, right? Okay, because you see, Z is not 0 in whole alpha beta, including the endpoints. So Z at the point, let's say alpha, or Z at the point beta is never going to be 0. So C has to be 0, right? Because Y at the point alpha is 0. So that will imply C has to be 0. Is this okay? Now if C is 0, therefore Y of x by Z of x has to be 0, right? Or since Z is not 0 in whole alpha beta, it means Yx has to be identically equals to 0 for all x in closed alpha beta. Okay, that's a contradiction again. Okay, because we have assumed that Y is a non-trivial solution. See, Y is a non-trivial solution. Okay, a contradiction again. Okay, so this cannot happen essentially. Hence, we have that it will have to have a 0 in closed alpha beta. Is this okay? Yeah. Right. Now, as a corollary, now one thing, before we go on, you do realize it's like a 2-3 line proof, right? I mean, that was like the original proof of Sturm was actually 4-5 pages proof, very, very complicated, very big. But this is very, it's like very easy once you know Pico's identity. Clear? Okay. So now let's look at the corollary. Okay, so what is it? Now as a corollary, I am going to write down something called a Sturm's separation principle. Okay, Sturm's separation theorem, sorry, separation theorem. So what is it? It says that if y1 of x and y2 of x are two linearly independent solutions, okay, of y prime, py prime, sorry, let me write it properly, of 1, let's say. What is 1? 1 is this equation. Where is it? This is what? Py prime whole prime plus qy equals to 0. Okay, in I, in some interval I. Okay, then their zeros are interlaced. Interlaced means, what does it mean? That is, if alpha beta are consecutive zeros of y1, okay, then there exists exactly 1 0 of y2. Is this okay? And vice versa. So basically, between any two consecutive 0 of y1, there is a 0 of y2, and again between any two consecutive 0 of y2, there is a 0 of y1. Okay? So interlaced. So before we go on with the proof of this, let's look at a small remark. Let's say this equation, y double prime plus y equals to 0. Okay? What are two linearly independent solutions? Sin x and cosine x. Two linearly independent solution. Now you do realize that where is this 0? This is at n pi, and this is between n plus 1 pi, right? Pi by 2. Okay, so essentially what is happening is this. See, between any two 0 of this, there is a 0 of this, and again between any two 0 of cosine, there is a 0 of sine, right? So basically sine and cosine in this case are interlaced. Okay, so this is the kind of motivation you can think of this theorem. This is okay. So let us look at the proof of this. I hope you understood what I am trying to say here. Okay, so now see, let me okay, so as a since I am writing it is as a corollary, so basically what we are trying to do is we are going to use Sturm-Picon theorem here. Yes, okay. Now how do you use this theorem? What do you think can happen? See, the thing is, let's say since y1x and y2x cannot have common zeros. Okay, right. Then this theorem, what is the theorem? Sturm-Picon theorem. Okay, then Sturm-Picon theorem implies that the solution y2 okay, first of all, you do realize what are the equations here, right? What is the equation? Okay, so what you do is this. See, first of all, you pause this video, think about how to prove this statement. See, the equation which I am comparing here, okay, Sturm-Picon's theorem is basically a comparison theorem between two equations, but in this case, what are the equations which you are comparing? See, we are basically looking at linearly independent solutions of just one equation. Okay, so it's not two different equations, it's basically one equation. Yeah, and I am comparing two solutions of the same equation. Is this okay? Yes. So now the question is so the thing is this: you have to note that these two y1 and y2 cannot have common zeros. Is this okay? Why it cannot have common zeros? Think about it. Okay. So take some time, think about it. If you can't do it, I will do it at the end of the this proof one. Okay, so it does not have a common zero. Let's just assume that. Okay, then the Sturm-Picon's theorem, what does it imply? That the solution y2 of x has at least 1 0 okay, between consecutive zeros of y1. Yeah, see, y1 and y2 between consecutive zeros of y1, y2 must have a 0, and between closed alpha beta, but it cannot have common zeros, so it has to be in between alpha beta. Is this okay? Now if you interchanging y1 and y2, okay, y1 and y2, we see that y2 of x, okay, has at most 1 0 between two consecutive zeros of y1 of x, right? Okay, so what did we prove? We proved that it is basically, it has to be interlaced. So basically exactly 1 0 should be there. Here we showed that y2 has at least 1 0. Now if you interchange y1 and y2, you can say the exact same thing for y1 what you said about y2, right? Because it's not a problem. y1 and y2 is just any two solutions. Okay, so in that case, between any two consecutive zeros of y1, there will be at most 1 0 of y2, right? So if you interchange it, it will be exactly the same thing. So, and hence it has exactly 1 0. So between any two zero of y1, there is exactly 1 0 of y2. Is it okay? Right. Now I hope you have concluded why it does not have common roots. Let's say that alpha is a common root. Okay. See, if it has to be common 0, it has to be either alpha or at beta. So let's just say that alpha is a common root. So in that case, what is the Wronskian of y1 and y2 at the point alpha? Okay, you can check that that is going to be 0. And since at the point Wronskian is 0, so if they don't have common root, if they have common root, common root 0 0 zeros, okay, common zeros, then at the point alpha the Wronskian is going to be 0. Abel's theorem says that then it is 0 for all points, and if it is 0 for all points, it has to be linearly dependent, but it is given to be linearly independent, hence this is not true. Okay, I hope this clarifies everything. Okay, now the theorem is trivial. Now, so basically what we proved is the zeros are interlaced. Clear? Okay. So now we come to a very important theorem, and this theorem says that if you are looking, see here, as I told you, I was just looking for some interval I, right? I did not specify what interval. It can be bounded interval, it can be unbounded interval. Okay, but now I want to prove a theorem which will actually say that how many zeros can be there in a finite interval alpha beta. Okay, so the only solution, okay, of 1 which vanishes infinitely often in alpha beta alpha beta is the trivial solution. So if you have a bounded interval, right? So what you can show is the only solution. So in a bounded interval, let's say if you are starting with a non-trivial solution of that problem, right? It cannot have infinitely many zeros. So basically it is not going to be oscillatory. See, with finite zeros, there will be a finite zero, right? I mean, if there are like finitely many zeros, okay, so there will be a last zero. It has to be. But in that case, the solution does not stay oscillatory. So you can't say that solution is oscillatory. You understand? Okay. So in this case, what we have proved, we are going to show is only oscillatory. If you are looking for oscillatory solutions of the equation 1, okay, then the trivial solution is the only one. There is no other oscillatory solution. Okay. If you have to look for oscillatory solution of this equation, you have to look at it at whole of R. Clear? Okay. So what is the proof? Okay. So let us assume that the solution y of x vanishes, okay, infinitely many zeros. So with vanishes, so basically, let me put it this way: has an infinite number of zeros. Has an infinite number of zeros in I. Let's just put it that way. Okay. See, I is closed interval alpha beta, right? Closed interval alpha beta. Some alpha beta doesn't have to be anything. It's just some alpha beta, but it is closed interval alpha beta. And you see, let's say let this where this vanishes, there are like infinite numbers, right? Infinity such points. So basically, let xm, okay, be, so in alpha beta, this whole interval is in alpha beta, okay. So for all m in n, be such that y at the point xm is 0. Is this okay? For all m. See, it has infinitely many zeros, right? So what does it mean? It means that there are infinite number of points where y is 0. And those points are in alpha beta. So I can make a, I can build a sequence out of it. So xm is a sequence which always lies in the closed interval alpha beta, such that y at the point xm is going to be 0. Is this okay? Right. So you see, xm is a sequence in a compact set. Okay. And what happens to the sequence in compact set? It converges. Okay. At least up to a subsequence it will converge. Okay. So I will just write it as write this as the whole sequence xm. Okay. So it will converge to x star. Okay. Therefore xm converges to x star. Why? Because alpha beta is compact. Okay. Bounded sequence, Heine-Borel theorem, right? Bounded sequence in a closed and bounded interval, it has a convergent subsequence. So that convergent subsequence, let's just call it again as xm. Okay. So xm converges to x star with xm not equals to x star. Okay. Is this okay? Now you see, we will show that y at the point x star equals to y prime at the point x star is equals to 0. Yeah, this is what we are going to show. First of all, let's just see if we can do something like this. Okay, what is y prime at the point x star? It is nothing but limit h tends to 0, y at the point xm, sorry, not h, m tends to infinity, let's say m tends to infinity, y at the point xm minus y at the point x star by xm minus x star. Okay. Now I know that y at the point xm's are all going to be 0, right? It's always 0. It's just an assumption. Huh? Okay. What happens to y at the point x star? See, xn converges to x star, right? So that will imply y of xm must converge to y of x star. Why is it true? This is by continuity. That's the very definition of continuity, right? If xn converges to x, f of xn must converge to f of x. F is continuous if and only if this happens, right? Okay, so it is there. So that will imply that limit m tends to infinity 0 minus 0 by xm minus x star. See, xm minus x star is non-zero, so this is going to be 0. Is this okay? Okay, so what do you get? Therefore, y at the point x star equals to y prime at the point x star equals to 0. So y is such a function such that y at the point x star equals to y prime at the point x star is 0. Yes? So uniqueness, Picard's existence uniqueness theorem. Uniqueness theorem. What does it say? It says, you remember what does it say? That equation, right? The equation 1 along with this initial data. What happens to this? 0 is always a solution and it satisfies this y at the point x star, some point x star is there such that y at the point x star and y prime at the point x star is 0. So that will imply yx has to be identically equals to 0. Uniqueness. Clear? Okay. So it has to be, the solution has to be trivial solution. I hope this is clear. Very, very nice proof, right? It's very nice proof. Okay. And full of analysis. Okay. So what did we learn from this theorem? Essentially what we learned from this theorem is this. See, in a finite set, see, up till now, I did not, you see, I was telling you that in some interval I did not specify if the interval is whole of R or if it is closed bounded set or not. Is this okay? Why I did not specify is because if you have a problem, one, that sort of equation, self-adjoint equation, in a closed bounded interval alpha beta, closed bounded interval, that is very, very important, okay? Then you cannot have oscillatory solutions. Is this okay? It cannot be oscillatory. I mean, if it is like infinitely many, it admits infinitely many zeros, it has to be trivial. There is no other way. Okay. Please remember, this is working only because it is in the closed bounded interval alpha beta. Otherwise, this is not going to work. Okay. See, Heine-Borel is not going to work. So, this is very important. Okay. So, now what we are going to do is basically, how do you know that the differential equation 1 is oscillatory? So, how does one test if 1 is oscillatory? Where it is oscillatory? In I, which is 0 infinity. Okay. See, again I told you closed bounded. If it is closed bounded, it cannot be oscillated. So there is no point looking at it. Okay. So it is always in the unbounded domain. Okay. So now we look at our theorem. Let's call this theorem. I don't know what you call this theorem. So maybe Sturm-Picon theorem. Let's call this one as theorem 1 for now. Okay. And let's call this theorem 2. This theorem has also a name. This is very, very important theorem. This is called Leighton's oscillation. Oscillation theorem. Okay, Leighton's oscillation theorem. So for just for reference purposes, let me put it in a red. So that will, identify it as a very, very important theorem, Leighton's oscillation. Okay, right. So what does that theorem says? It says that if integral over infinity 1 by p of x dx, if this is infinity, okay, and integral of q of x dx till infinity is infinity. Okay, so basically you need to have two blow-offs, 1 by p and q. They should not be summable. Is this okay? They should not be summable. Then 1 is oscillatory, where oscillatory in 0 infinity. Is this okay? It's not a very difficult thing to understand. The theorem is quite clear. It says that if 1 by p and q, if they are going to infinity, then the theorem is oscillatory. Okay. So as an example, so before doing the proof, let's just look at it. See, what is the one equation which we know is oscillatory, the most famous equation, y double prime plus y equals to 0, because y equals to sin x, y equals to cosine x is the solution of this problem. So we know that this is going to be oscillatory. Okay, what is p here? P is 1. What is q here? u is 1. Okay, if you integrate 1 dx over infinity, it is going to infinity, and again the same thing will happen with p. So you do realize that this is very natural assumption. Is this okay? Right. So basically what it is saying is this: if these assumptions are satisfied, then 1 is as oscillatory. Is this okay? It may happen that something is oscillatory, but these two conditions are not satisfied, or at least one is not satisfied. It may happen here. So please remember that it is not like a necessary and sufficient condition. It is a necessary condition. So basically, it is a sufficient condition. It says that if this and these two conditions holds, then it is oscillatory. That's what. It is just sufficient. Okay. So let's look at the proof. Now I am not going to do the whole proof. Okay. There are some parts which I want you to check yourself. Of course, I will put it in an assignment also. So because this actually involves a small trick, which is you should at least know. So let y of x, I have to show it is oscillatory, right? Okay. So let's start with a non-oscillatory solution of this equation. Let y of x be a non-oscillatory solution of 1. Solution of 1, right? Okay, which we assume to be positive in x naught infinity. Okay, x naught is positive. Okay, why we can assume this? See, think about it. If yx is non-oscillatory, it means that it has a last 0. Okay, so after some time, let's say 0, after some time some xm is there. Okay, x naught, let's say x naught. After x naught, there is no point where y will be 0. Yeah, this is the last 0. So since y is positive, this is the last point where y can take 0. After that, it has to be either positive or negative, right? Yes, but it can never touch 0 anymore. This is the last 0, x naught. Okay, so we are just assuming it is positive after that point. Okay, right. I hope this is clear. Huh? So now check this part. This part I want you to check. This is something called a Riccati's equation here. So the Riccati equation. See, this is a tricky proof. Equation. I will use the solution of this equation. Okay, z prime plus q of x plus z square by p of x equals to 0 has a solution z of x, okay, in x naught 0 infinity, sorry, x naught infinity. Okay, so you have to check this. See, the thing is, this is manufactured stuff. Let's just put it this way. Okay, there is no apparent, how do I put it? I mean, it's not quite obvious where we are getting this from. Okay, and the how do I put it? The motivation behind getting this particular equation is not quite clear. Even for me also, I am not quite sure how Leiden actually came up with this equation. Okay, but the thing is, he used this Riccati's equation, and what he did is, basically, once you have that, you know that there is a z in this interval such that z satisfies this equation. What happens there? Now you see, you integrate this problem. What happens if you integrate? It becomes z prime becomes zx minus z at the point 0. That will happen. Right? Sorry, z at the point x naught. So it starts from x naught, right? Z at the point x naught. Okay, so let make it equal minus integral q of t dt, and what is the interval? Interval is x naught to x minus integral, you see, z square t dt, t by pt dt, and the interval is x naught to x. Is this okay? If we do that, now you see, since q of t, the tail part of qt, this blows up. Okay, there exists x1 which is greater than x naught, such that z of x naught minus x naught to x z square t by pt dt. One second, sorry. So basically these two term minus x naught to x qt dt. Okay, this is negative. This is okay. See, z of x naught is some number, 5, 10, 100, 1000, million, doesn't matter. But after x1, so you know, you can always find x1 such that for x1 greater than x naught, okay, what will happen is this, the integral, see this is blowing up, right? So after some times the tail part will be very heavy, so it will be very large, right? So z of x naught will be dominated by this because of this negative sign. That is why it is negative. Is this okay? So this holds for all x in x1 infinity. This is okay. For all x in x1 infinity, you can say this. Thus what do we have? We have zx. Okay, this two term is negative. So basically it means it is dominated by minus integral x naught to x z square t by pt dt. This is okay. Pt dt for all x in x1 infinity. Is this okay? Now what we do is basically we write this as r of x. Okay, so define r of x. Okay, what is r of x? It is x naught to x z square t by pt dt. Clear? This is for x in x1 infinity. x1 infinity. If this is the case, then z of x is dominated by minus r of x. Is it okay? And what do you have? R prime of x. This is okay, right? Zx is less than equal minus of r of x. See, r is this, right? So zx is less than equal minus r of x. This is what I wrote. I hope this is fine. And r prime x. What is r prime x? This is nothing but z square x by p of x. Clear? Okay. Now that is greater than r square x by p of x. Is this okay? See, z plus r is negative, right? So z square minus r square. So p is positive. P is positive given, right? That's what we are always assuming. See here, in this whole this, how do I put it? The whole study of this, yeah, we of course always assume p is positive, because otherwise p can be 0 and then we have problem. You do realize everywhere we have checked, you see, we have always assumed that p is positive, you see. Okay, so p is always positive. Please remember this, very very important. Okay, right. So if positive, if p is positive, of course z square is greater than r square, right? Okay, so if this is the case, what we have is this, so this is holds for all x between x1 and infinity. x1 and infinity. This is okay. Now if we integrate this thing, okay, integrate from x1 to infinity, we have minus r evaluated at infinity. So basically I should write it as limit r tends to t tends to 0 1 by infinity 1 by r of t, but I'm just writing it like this. Okay, I'm just being lazy here. And r at the point x1 is dominated by x1 to infinity dt by p of t. Is this okay? Yeah, we can do that, right? We can just integrate it. See, r prime by r square is greater than 1 by px. So, and then I can use this thing, fundamental theorem of calculus, to get this. Is this okay? Therefore, integral x1 to infinity 1 by pt dt is dominated by 1 by r x1. Is it okay? See, this is a negative term, so it's that you can just throw that away, right? So it is dominated by 1 by r x1, which is finite. Okay, now that's a contradiction. Why it is a contradiction? Because this is our assumption that the 1 by p is not summable, but here it is showing it is summable. You see, the assumption is 1 by p is not summable. This is okay. So that actually concludes Leighton's oscillation theorem. Okay. So let's look at a small application of Lighten, and then we are going to finish this video. So let's look at a small example. So let's say that for all A sufficiently A, there exists x naught large such that you see 1 plus 1 minus 4a square by 4x square. Clear? This is greater than half for all x greater than x naught. Clear? We can prove that, right? Given any a, I can always choose a large enough x naught such that this happens. If you are not convinced, please check this part. It's very easy, not very difficult. You can do it yourself, absolutely no issues. Okay? If you are not able to do it, what you do is you break everything up. You just break everything up and after that put it together. Okay? You can get this inequality, absolutely no issues. So you can show this, that for any a, doesn't matter what a is, for any a, you can actually find a large enough x naught such that this happens. Clear? Okay. And hence integral till infinity 1 plus 1 minus 4a square by 4x square times dx. This is infinity, because see, this expression is always greater than half no matter what x is. After x large enough, this is always greater than half. So if you are taking the integral up till infinity, it is always going to diverge, right? That's just the case. So therefore, so this implies that the equation y double prime plus 1 plus 1 minus 4a square by 4x square times y equals to 0 is oscillatory. Okay, see, by looking at it, you can't really say if it is oscillatory or not. But the thing is, on Lighten oscillation, you can use directly and you can say this is oscillatory. Okay, so this is a beautiful theorem which you can prove using Lighten. So with this, we are going to finish this video.